Hi everyone. So to start with a couple of notes, we want you to start giving every answer a value in a unit, which you guys are comfortable with. But now we're also going to add that you need to give it an identification. So 6 moles is no longer good enough. You need to say 6 moles of sodium chloride, and obviously proper sig figs. As always, just another reminder, even when we don't explicitly say it in the directions, you should always show your work, unless it's something where you're getting a number off the periodic table type thing. So if you can show your work, if you can show support, you should do it, especially for dimensional analysis. It's going to become very, very important. If you don't show your work, I can't give you credit. Okay? And we're also going to have you start doing a reality check. So this is pretty much, I want you to look at your answer and think, is this bullshit or does this make sense? Yeah. So if you get a really, really big number where you're expecting a regular, like 2 or 3 number, you should probably double check your work. A lot of times this will come up with calculator. Your work will be fine, but you'll have put it in the calculator wrong. So be careful. All right, so to jump right into our notes. So the concept of a mole is useful because it relates quantities of chemicals that we can measure to the amount of molecules and or atoms that's in that amount. So to put it really plainly, this is essentially that the mole relates the large scale and the tiny scales, right? So it's something that I can measure and the little tiny constituent parts of it on the atomic scale. So there are 3 things that I want you to take away from this. There's going to be the concept of a mole, Avogadro's number, which I'm going to abbreviate is N sub A because I'm lazy. You guys can't do that yet. And then we want to talk about the difference between molar mass, that's a V, and atomic mass. Okay? So let's go back up to the mole. Remember, a lot of times people get scared about a mole because they don't know what it is. It's literally just a number. If I say a dozen, you know it's 12. If I say a pair, you know it's 2. Right? It's exactly the same thing. It's just that a mole is really, 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 really big. So it is just a number. Don't freak out. So if I were to give you a reference point, because it's so big, there are 7.8 billion people in the world. Okay? So if I were to write this out, that's how many people are in the world. This is a mole. It is unfathomably large. Okay? So if I were to say how much of a mole is the 7.8 billion people in the world? How much of a mole do we have of people? That's incredibly tiny, right? So all these zeros it's huge. So remember that there's a bunch of zeros. This is going to be a positive exponent. Okay? If it helps, think of October 23rd. Same way we have Pi Day, we have Mole Day. So October 23rd is positive. Make sure you know that. And this is going to be any number of things, right? Pumpkins, dolphins, puppies, pens, whatever. The same way that you can say I have a dozen donuts or a dozen cats or a dozen cars, doesn't matter. This doesn't have any particular association with a thing, right? This is things, particles, atoms, dolphins, planets. So this is what Avogadro's number is. Now, if I wanted to relate the large scale or the measurable scale and the tiny scale, I wanted to go back and forth between these because maybe I have one number, but I want the other one. This is when we use Avogadro's number. Okay? Just because we gave you this shiny new tool doesn't mean you need to take that same hammer to everything that you come across. Okay? Just because you have a new tool in your toolbox doesn't mean that you immediately pull it out. Make sure you're thinking about when you're using it. So we'll use Avogadro's number whenever we're going from moles back and forth to atoms, or if we're going from grams back and forth to AMU, right? So I can go from atoms to moles and moles to atoms. Now, usually we are going to ask for a number of atoms or some number of moles that's in some mass, right? Some amount. Another way we'll ask a lot of times is how many moles are this number of atoms? Or how many atoms are in this many moles? And then occasionally we'll ask for you to go between grams and AMU, or some combination of these. Yeah. So if you get pretty comfortable with how to go back and forth on these, you'll be fine. So we've got molar mass versus atomic mass, right? You're very familiar with these. We've used these terms a lot, especially molar. So if I were to have you look at the scale, not necessarily the actual scale, right? Like molar mass is something I can measure. You can go into the lab and you can measure out 4.8 grams of copper, right? And that is like a measurable amount. So we would say that this is the large scale compared to the atomic scale, yeah? So like a macro scale. Atoms are incredibly tiny. They're the micro. There's another one actually that is molecular mass. Okay? Remember the difference between an atom and a molecule is that a molecule is multiple atoms bonded together. All right? That's it. So this is also going to be the tiny scale, right? So measurable and then things that we can figure out, right? So if I were to look at the units for this, molar mass, anytime you have molar, this is literally saying the mass of a mole. So I want some mass per 1 mole, okay? And the mass that we use to go with moles that's appropriate is grams, okay? If I have an atomic level, then I'm going to want something per atom. This is literally the mass of 1 atom, okay? So a mass number, or excuse me, a unit of mass that we use with atoms is called AMU. Sometimes you'll see it as U or as Daltons. They're all the same thing. They all mean the same thing. I'll usually write AMU. So AMU and grams, both of those are units of mass, right? And then some per some package, per some mole, per some atom. So the same way that these are molar mass is per mole, atomic mass is per atom, you can guess what molecular mass is. This is literally saying the mass of 1 molecule. So this is also on the tiny scale. The only thing that is different is that instead of having 1 atom, I now have 2 atoms that are bonded together. Yeah? So this is also going to be AMU. Not sure how terrible my handwriting is. Per molecule. Okay? You need to be very careful. In the next couple of weeks, you're going to be asked about different ones of these. And if you don't give the right unit, then your answer is not correct. Okay, so if you're asked about molar mass, you need to give us grams per mole. If you're asked about molecular mass, you need to give us AMU per molecule, right? Be very careful with what you're doing. So if you want to take a break at this point, I'm going to go over a couple of the problems on the worksheet just for, I guess, a demonstration of this. And then I'll give an example, and then I'll give you a couple more notes about the worksheet of what we want to see and what we don't want to see. So you can take a break here. Okie dokie. So if you remember, we were saying earlier that Avogadro's number of atoms or particles or dolphins or molecules or puppies, all of that equals 1 mole, right? And remember that that's 6.022 times 10 to the positive 23. So if we are asked how many atomic mass units are in 1 gram, well, gram is on the same scale as mole, and atomic mass units are on the same scale of atoms, particles, and molecules. And this has actually been set up so that there is exactly the same proportion between a mole and Avogadro's number and a gram and AMU. So 1 gram and 1 gram, there's 6.022 times 10 to the 23 AMU. Okay. Now, one of the things that I didn't necessarily talk about on when we were talking about molar mass versus atomic mass versus blah, 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 was that moles and molecules are both able to be the coefficients in a balanced equation. The difference is the view, right? So if I have a 2 in front of some sodium chloride, I can either say that there are 2 moles of sodium chloride, if I'm looking at the measurable bigger scale, or I can say that there are 2 molecules of sodium chloride, right? And that's looking at the very, very tiny scale. And so if I have something really tiny, at an atomic scale, I can scale that up exactly to the big scale, okay? This is really similar to like some building, let's say the Buckingham Palace, and then you have a child's scale model of the Buckingham Palace, okay? So mansion for ants. All right, so 1 gram is the same thing as Avogadro's number of AMU. 1 mole is Avogadro's number of things, right? Usually small stuff. So when I read this out, this is how I'm going to prove that the atomic mass and the molar mass, well, the average atomic mass and the molar mass, the number that's on the periodic table, are the same number, right? It just depends on the unit. So if I have an atom that weighs 3 AMU, I want to know how much of a mole is it in AMU and then in grams. So what I want to do is I know that I have 3 AMU per atom, and I want to get to how much of a mole of it is in AMU. So I already have AMU. I'm going to put 3 AMU for every 1 atom of whatever it is we're looking at. But I need to get rid of AMU. I don't want to get rid of AMU. I want to get rid of atoms. That was dumb. All right. I need to get rid of atoms. I don't want it. I put it on the opposite side. And I know I need to get to how much AMU is per 1 mole. Remember, per is that dividing sign. So I can put per mole. So I'm going to have mole on the bottom. So what that means is that my atoms cancel out, and I'm left with AMU per mole. Okay, so my units work out. Now I can put my numbers in. So every time I have atoms is really, really tiny compared to a mole. So I want to put the really, really big number with it. Okay, so this is going to be Avogadro's number. Okay. Remember, N sub A is 6.022 times 10 to the 23rd. And for every Avogadro's number of atoms, I have 1 mole. So if I do that math and I put it in my calculator, don't round, I have 1.807 times 10 to the positive 24 AMU per mole. Okay, so that's my answer to the first one. But then I'm also asked, how much is it in grams? So what I'm asked is, how many grams does this mole weigh? So what I can do is I can just change my AMU to grams, right? I don't need to restart everything. I can see that there's a connection directly between AMU and grams. We just talked about it. So if I were to start with the same number, 1.807 times 10 to the 24th AMU. Now you may be tempted to put per mole on top, but don't do that. 1 unit on top, 1 unit on bottom. Okay. All right. So I want to keep my mole, but I need to get rid of AMU. So if I want to get rid of AMU, I put it on the opposite side. And I want to get to grams. I know I can go from AMU to grams in one step because of this right here. This is the conversion that I'm going to use. Okay. Remember, AMU is super small, grams is really big, and so what I can do is I can put the big number with the smaller portion. Yeah. So Avogadro's number is going to go on the bottom for every 1 gram. So I know that if I have an atom that weighs 3 AMU, it weighs this ridiculous amount of weight per mole. So AMU is super, super small, and mole is something that we can actively measure. So it makes sense that this number is really, really big, right? So this answer is not bullshit. And then if I'm looking at it and I get rid of my AMU, well, now I've scaled up my grams as well. So now I have grams and mole. And both of those are similar scales, right? I can measure grams, and grams and moles are both bigger scale. So if I were to do this math now, 1.807 times 10 to the 24 divided by Avogadro's number, I want you guys to do this in your calculator. Every one of you should do this because I want to make sure you know how to use the EE key, right? So you'll look for something that looks like that. Or if you have a Casio, there's going to be a button times 10 to the, right? You need to use parentheses. The EE key takes care of parentheses, so I prefer it. But if you don't have a calculator that has it, you've got to be comfortable using parentheses, right? If I take this and then I divide by 6.022, I also need to divide by times 10 to the 23rd. Okay, gotta be careful. So if I do this properly, and you're doing it too, then I get 3 grams, not AMU, 3 grams per mole. So I have just proven to you that we went from AMU to a different color, because why not? I have just gone from AMU per atom, where 1 atom weighs 3 AMU, and I've shown you that that's exactly the same thing as grams per mole. It's the same number, right? Not necessarily the same thing. So if I have an atom that weighs 3 AMU and I have a bunch of atoms that all weigh 3 AMU, it balances out to where, or averages out to where every mole of that same element, whatever I'm looking at, weighs 3 grams. Okay? So AMU per atom is equivalent, well, not equals, equivalent, excuse me. The number is the same, right? AMU per atom to grams per mole. Remember, AMU per atom is atomic mass, so this is that average atomic mass, and grams per mole is molar mass. Okay? So a couple notes. First off, know how to use your EE key, or know how to use parentheses, know how to do times 10 to the EE key is a lot faster whenever you're taking an exam. Some more notes is that on number 3 for your worksheet, you don't need to do work. We just did the work, right? So you do need to have this written out on your worksheet, but you don't have to do the work for number 3 because it's the same goddamn thing. Don't do the work. That's a waste of time. But you do need to read the directions and follow them preferably. A lot of people will miss it. If you don't follow the directions, can't give you full credit, right? Because we're telling you to do something. If you don't do it, you don't get credit for it. From number 4C through the rest of the worksheet, you have to show your work. You have to show dimensional analysis, right? And then your answer for 4E should be the same as your answer for 5A, and you should think about why that is, okay? All right, you can pause here. I am going to do an example in just a second. So if you don't care about the example, then you don't have to watch it, but it really helps you figure out how to approach problems with moles. Alrighty, so I made up a couple questions here. So you guys can do this in your head, all right? You know how to do this. You know exactly how to figure out that if a box full of puppies has 8 puppies and you have 2 boxes, that's 16. You know how to do this. So if we were to break it down into dimensional analysis, you want to look and see what information you're given, right? So I know that each donut has 25 sprinkles, right? Let's use the purpley color. So if I know that one donut equals 25 sprinkles, we're going to assume a machine spits them out or something out. And then we're told that we're going to buy a dozen. So we're asking how many sprinkles are there in total if you buy a dozen donuts. Well, I know that a dozen of anything is 12. Okay. So this is implied, this is explicit. All right. Okay. So I'm told that I bought a dozen. I don't want dozen my final answer, right? What I'm being asked is how many sprinkles do I have at the very end? Okay. I want to get to the point where I just have sprinkles. So a dozen donuts. I need to get rid of a dozen. I want to put it on the other side. Okay. Notice my colors match up. So if I have a dozen donuts and I'm trying to get through to sprinkles, then I'm going to say, okay, a dozen is 12 donuts. Okay. But I don't want donuts in my final answer. I just want sprinkles. So if I don't want donuts, I put it on the opposite side. Donuts and sprinkles. Okay. My units all work out. I know that I've done this right. Now the only thing I have left to do is to just plop in the numbers. All right. So a dozen is bigger than donuts, so it should have a smaller number. Also, you can see this equal sign as sort of that cross here. So 1 goes with the dozen, it needs to stay with it. Okay. If you were to get confused, you would think about the fact that one big thing equals a bunch of little things. And then 12 is on the other side, so it goes on the other side. And then however many donuts I have, 1 goes with donuts over here, 1 has to go with donuts over here. Also, I know a bunch of sprinkles go on 1 donut. 25 goes with the sprinkles, 25. So this is essentially what is 1 times 12 times 25. This is going to be 300. You can check me if you want. So 300 sprinkles. Okay. Technically, all of these things are counted. So it would be however many units you wanted. Or sig figs. Gosh. All right. And then I want you to box your answer so it's easier for me to see. Okay. So if you see the next question, this is the whole reason that we're doing this example, right? Everybody's freaked out when a mole comes into the play. It's exactly the same thing. It is exactly the same setup, same concept. Don't freak out, okay? So I'm told that I buy a mole of donuts because I have lots of money. So if I have 1 mole, I know I'm still working with a lot of this up here, Remember that a mole is 6.022 times 10 to the 23rd of anything. So I don't want mole in my final answer. I'm still looking for sprinkles. So I'm going to put mole on the opposite side. Well, a mole is 6.022 times 10 to the 23rd of anything. So I could put dolphins up here or whatever. It doesn't help me. So if I put instead donuts up here, gotten rid of my mole. And then if I use the same, it's all the same, right? This setup looks exactly like this setup. Don't forget. So I don't want donuts in my final answer. I'm going to put it on the opposite side. And I know I need to end up with sprinkles, and I have something that connects sprinkles and donuts, right? Okay, my donuts cancel out. I'm left with sprinkles. I know my setup is correct. Now that I know my setup is correct and all my units are set up, now I'm going to go back through and I'm going to put numbers in step by step. So mole is really, really big. 1 goes with mole. 1. And then Avogadro's number, 6.022 times 10 to the 23rd, donuts. And then for every donut I have, I get 25 sprinkles. Okay. So this is going to be 1 times Avogadro's number times 25 divided by 1 divided by 1. Anytime you have numbers on the bottom, you've got to divide by them. Okay. You can use parentheses and do top divided by bottom, but you need to be careful because you can't do this times this times this divided by that times that. Okay. If it's on the bottom, it needs to be divided. However you get there. So if I do 1 times Avogadro's number times 25, I get 1.6022 times 10 to the 23rd. Never mind, I can't do math. That was supposed to be times. So this is what you would put in your calculator. My answer is not that. It's 1.50550000 times 10 to the 25th sprinkles. So I want you guys to get used to giving me a longer answer with a couple more sig figs than what you think you might need. And then look at the sig figs and kind of do this sort of thing, where you can still see what your original answer was. Don't erase it. But then I know that the answer you're giving me is in the box. Cool. So if we were to say maybe these 25 sprinkles, they put the 25 sprinkles on it by weight. So they put a donut on like a scale, and then a machine sprinkles however much powdered sprinkles or whatever until the scale shows a certain amount. That would be something that's measured. So in that case, if it's measured, this would be 2 sig figs. So my answer would be 1.5 times 10 to the 25th sprinkles. Okay, that's just an example to show you that I want you to keep the extra sig figs and then go down here and box this answer. Because if I were to ask you a follow-up question that uses this, you have to use the full answer that's unrounded, okay? Because you only want to round at the very end. So this is kind of like a stop off. So if I have part A and this is my answer for part A, but then I need to continue using the full thing for any subsequent parts, okay? Thanks for hanging out with me. I know that was painful. Bye.